Professors. Hello there. Professor Artomlensky. Good morning.
Hi, Professor Kahng. Can you hear us?
Yeah, definitely. Good to
Oh,
hear your voice.
all right. Great, great. Yes, thanks a lot for joining today with your interesting talk. We're all looking forward to it. So I just want to give a couple of introductions. So Professor Kahng, he is with Incheon National University. Incheon is one of the largest cities next to Seoul in South Korea, and this university is very well known. And Professor Kahng, he worked for numerous institutions on mostly communication and radar theory, including for defense. So we're all looking forward to Professor Kahng for your talk. Thanks for joining. Would you like to add something?
Yeah. May I share the screen with you? That's fine.
Yeah, yes, please. Yes.
Yeah. Yeah. Could you allow me to share my screen? Here you go. Is there any trouble in seeing my presentation material there? Can you see that? Yeah. The title page of my talk. Can you see the title of my talk? Professor Artomlensky,
Just one moment, please. I'm trying to full screen it. Just 1 second.
yeah, please give me a cue when you're ready. I think it is working.
All right, Professor Kahng, we are ready if you're ready.
Yeah, good, good. Uh, yeah, may I start it now?
Yes, please.
Oh, good, good. Yeah, yeah. First of all, I'm really thankful to Professor Artem Lensky for giving me this opportunity. What is my honor to say hello to everyone in New South Wales, Canberra. But unfortunately, I cannot come there in person. But actually, the most of the content. Uh, I'm not going to deal with it in detail for 1 hour. For the rest of the things I cannot cover till the end of this talk, hopefully I will bring it to you for a later visit to Canberra. It's going to be a good excuse for me to join you for academic and research collaboration and other things. Um, yeah, the first page shows you the title I was sending to Professor Linsky. That is the electromagnetic phenomena used for satellite communication and radars, especially direct waves and their reflection. Um, I'm not going to give you what all the details of what electromagnetics what gives you at the end, but uh, our objectives are very clear. we want to have quality communication, and we want to have good data based upon quality radar systems. There are many components that make things possible in terms of the satellite communication and radars. All the components and all the blocks are very precious. What collaboration between a software block and hardware block, what I'm going to tell you mostly is the hardware part. Electromagnetic phenomena, uh, as mentioned here, this is an intangible thing, but actually it happens and it is real, even though we cannot sense with our eyes or with our ears, but actually it forms the link between the transmitter and the receiver or the controller on the ground to the drone. You have seen, observed indirectly the electromagnetic phenomena in your daily lives. You will see a number of examples related to satellite communication radars. Hopefully, you can enjoy the pictures. I just talk about a little bit of the mathematics, but most of the mathematical expressions coming from physics are well understood on the basis of your old experience on that. Before getting started, yeah, you see ICEE top of the center of this presentation material, a slide, International Conference on Electrical Engineering 2026 is going to give you a good chance to visit Seoul, the capital of Korea, where I live. Next year, July, we are ready to welcome you if you bring things about software security, AI applications. Though this deals with electrical engineering stuff, Korean electric power company these days is changing to kind of industrial professionals of AI applications. And Amazon Web Service will join us, according to the manager. So it's going to be a fun time for you to give presentations on what to do, and you can hear what they do and have a good time to exchange thoughts and interests using the time. But before ICEE happens, you can knock on the door of my office because my university is located in Incheon. I'm going to show you how, what convenient for you to approach. There are pictures arranged in the first slide. The first one is because electromagnetic phenomena I'm going to talk about today are mostly about scattering fields and the electromagnetic linkage with regard to cars, airplanes, and vessels. But actually, you can extend this to urban channel model, which guarantees the quality of a mobile communication like that. Yeah, top left, this is the surface current density induced on the surface of a car, or this can be what transformed to the head of a UAS, because I'm specializing in electromagnetic application for UAS radar systems. So what it is not hard to take this matter to the fields of a radar or sensing systems of drones. And you also see drones, one, two, three, but actually one structure that changes the angle of view. Then radar cross section. Radar cross section is a kind of a yardstick to examine how much of the how strong the reflected field from the flying vehicle is. So angle, in terms of angle or in terms of frequency, you can examine the radar cross section. So the larger the object, the larger radar cross section will be. Then what it is clear for you to detect the target which is away from you. And also another picture on the top right, yeah, top left that is a car, and top right is another type of vehicle, but it's flying. That is another example of a drone. And on your the right bottom, it is a car which is put it into the CAD program. Actually, I myself is a program maker to analyze the electromagnetic performances or characteristics of cars with the antennas or vehicles in the air about antenna performances like that. Yeah. So I am welcoming you to Korea, especially in Incheon National University. This is the outline of my talk, uh, with starting from Incheon National University, is introduced very briefly, and it is followed by the detailed topic subjects like work to know radio physics or electromagnetics of antennas and sensors on airplanes and ships, and work to make radio devices for the vehicles. All you have a high specialty in software fields. Actually, what you produce should be delivered through the wireless communication mechanism. To do that, all the things from different or separate blocks should be cooperated well. Yeah, so the devices, all device makers all the time have in mind what kind of types of information you would like to deliver in terms of a frequency and bandwidth, and how far the distance between the transmitter and receiver kind of thing, and the speed of the data transmission, etc. And it is followed by baseline or basics of the radio physics and radio frequency devices or wireless devices, and experiments to verify the baseline. Um, since most of the research and students have been busy with software field, I should let them know what kind of simple experiments carried out to investigate the electromagnetic phenomena, especially in terms of direct wave and reflection. Reflection is going to be the key to understanding radar systems and mobile communication, multi-fading and multi-reflection stuff. And the last two parts are pop quiz questions and Q&A, but pop quiz questions are not that tough. During my talk, you will get some hints, and I can take you directly to the pop quizzes, but I don't think they are going to be very tough for you. I'm going to reveal the secrets of how to handle that. Yeah. And before moving to the next slide, you now see the CAD or the picture of my antenna system that was recently developed with a local defense company to deal with the radio frequency signal transmission and exchange between the ground terminal and the defense military satellite. So what it is a tangible thing, even though it handles electromagnetic wave, which is intangible, but actually all they are real things, definitely. And on your right hand side, you now see my book, co-authored with the well-known IEEE Antenna Propagation Society fellows. So you can refer to this book for detailed information on how antennas can be can get smart in terms of the use of the metamaterials or what advanced technologies. Um, the first page in the main part of my talk tells you where we are. This is Seoul. Actually, this is a zoomed in picture of the South Korea. You can't miss Incheon International Airport because this is the gate for foreigners like you to come in and go out of Korea. It is very close to Incheon National University, where I am giving the presentation now. Yeah, this is a bird's eye view picture of the campus. The campus is quite new, because we moved from the old city of Incheon metropolitan area to a new area. So it is easy to access my office. You're all very welcome. And here I teach and train students uh, um, whether they pursue software field or hardware field uh, from the freshman years till the senior year, they should meet me and they should go through the classes I teach. Most of the classes I handle are electromagnetics, physics, microwave engineering, antennas, including metamaterials, and numerical analysis. I myself still handle programming. I try to encourage the software engineers to be interested in hardware and the interconnection between the hardware and software field. And I have antenna test facilities. This is one of them. Especially, you now see long antennas, which are low periodic antennas to test radio frequency uh, signal from the tag antenna. The RFID, radio frequency identification. The tag, the energy is scattered to any arbitrary direction. That's why multiple antennas are required to test the radio frequency signal there. And this is one of the examples of many. Now you see four different kinds of vessels or vehicles, aircraft, especially the fighter, on the left top and right top, that is passenger airplane, and on the left bottom, that is a military vessel on the sea, and on your right bottom, you now see a helicopter, uh, but except the beam pattern or electromagnetic field distribution like this from the antennas mounted on the helicopter. All these three other examples show you the electric surface current density on the surfaces of their bodies. It is really important to calculate. All these are the results of the electromagnetic computation using numerical analysis. In the past, they couldn't handle very complicated geometries like these, but these days, with the help of the advancement in computing and the advancement in numerical analysis, computational electromagnetics, we can characterize the surface current densities. Surface current density is the key to understand the scattered wave. Scattered wave can be understood in terms of reflected field to the radar system or for communication. So you now see the color code. Red means the hot spots. That's where antennas are mounted or in the vicinity of the antennas. Dependent upon different frequencies, they have different patterns in terms of surface current density. And on your what this different from the other examples, what this shows you the surface current density, but the resultant far field patterns on different frequencies are given to you. So for military areas, you need to talk to the vehicles like these, dependent upon the distances or ranges and the power you give. You beforehand you should analyze the electromagnetic characteristics like these. Work to make radio devices. I have developed two transponders for two satellites when I was working for the State-run Research Institute, but it has been continued to what I do today. I am the director of the Korean government-sponsored IT or Information Telecommunication Center. So if you want to exchange students, what I'm really glad to have them trained for understanding hardware for communication and radars. And well, we develop antennas and radio frequency components and radar systems and test them in reality like this. Actually, this is a good to encourage the passersby to be interested in what we do too. And also, we have a good simulator to understand how we can optimize the route between the ground terminal of one city through the low Earth orbit network to the ground terminal at the other city like that, and also considering the what coverage of the satellite, checking the power, output power of antennas and beamforming performances. And also, I'm working on civilian areas and business sector too. You know, LoRa. LoRa is long range communication compared to the frequency dealt with in satellite communication. LoRa and Wi-Fi communication use the frequency bands, which are way lower than that of the satellite and radars. But what they don't have to adopt that high frequency, and the lower the frequency band, the smaller or narrower the bandwidth. So that's the price you have to pay for when you bring the lower frequency. Lower frequency stuff is less expensive and very convenient, but the data transmission rate is relatively lower. One hint for your quiz question is received radio frequency power is inversely proportional to the square of the distance. Distance is defined as that between the transmitter and the receiver. So please keep that in mind. But the quiz question is related to this is not hard to handle. By the way, this is a typical shape. I took this picture when when I had to carry a project from a research institute. The commercial what antenna systems or devices, the power is not enough. Actually, why the reason I mentioned the inverse proportionality of the distance, a square of the distance to the received power, we should get over this path loss. It is called path loss. That means as the distance increases, the received power goes down. So by having good antenna here means the good directionality or good gain. So by changing this commercial antenna, these antennas are on the market. You can take them and put them and plug them into the LoRa devices. All they are commercial, but I had to change this antenna to my antenna. I could increase the gain. As you see here, the black line, the left, the ordinate here, the vertical axis means received power, signal strength. So as distance increases, that means the transmitter, say for example, transmitter is just grounded here, and we move the distance between the RX receiver and the transmitter, you experience the radio received signal strength goes down very drastically like this, the green, the blue curve. But compared to the blue curve, ours gives you stronger power at the receiver, even though at the same distance from the antenna. But the antennas which are substituted for the other antennas should not be heavy, should not be big. So we develop our antennas to increase the received power level. So you find the benefits of LoRa communication service. LoRa doesn't require the AP or access point antenna between the transmitter receiver sides. Mobile communication network requires, cellular phones. need many access point antennas, but LoRa communication service or protocol doesn't require the AP or relay antennas, but there's a limitation. You can secure for quality communication just 1 kilometer, but different from what they their advertisement. Actually, the distance is not guaranteed. That's why I had to develop my own antennas. And also, a very similar idea was applied to Wi-Fi communication-based alarming system to let people or walkers or workers know cars are coming on the road like that. And also, we changed the old antenna or conventional antenna with mine. Then we could increase the distance or communication range from the transmitter to the receiver side. They are workers who wear the helmets for safety. They all the time on the alert and should be informed of what is coming. So it is good to use and practice for public safety. And also, I have been developing wireless power charging devices, which is dubbed as wireless power transfer structure. So I could turn on the LED light, which is away from the transmitter by 3 meters or 5 meters. But for communication, 3 meters, 5 meters don't matter that much. But in wireless power transfer, it really matters. So at a given frequency, such as 2.4 gigahertz ISM band, we could increase the antenna gain and we could turn the LED. Before us, they failed in turning on the LED in a long distance, just what within the 1 meter, but I can make it for 3 meters and 5 meters like that. And also, I could, with my associates, what give the function of the beamforming too. Beamforming is required for handling the moving vehicle like that. And also, we developed the radar or antenna test antenna measurement system for a drone. So if you are interested in working with me, you can visit Incheon. What Incheon, right in front of my research center, there's a wide area, but Australia has a much wider place to test this kind of thing, and I can dispatch my staff members to help you to work on antenna measurement or electromagnetic field measurement. And also, you must be interested in this kind of drone-based antenna measurement system. Why? In Air Force or airport instrument landing systems, or simply ILS, they is a huge system. But how can they characterize the electromagnetic field distribution or power distribution in the open area? To do that, we need to dispatch the drone which holds the antenna. So one of my research works is to develop um, antennas for drones. Drones, well, because it is limited in the weight or mass, and it is limited in the range. So we need very small antennas. So it's going to be introduced later. So ILS, which is practiced in airports and air forces. Um, Before talking about antennas for drones, I also developed antennas for cars. You know, a shark fin antenna, if you open the cover, it is a very complicated structure. Why? Within a very confined space, you need multiple antennas for different services, such as LTE and the V2X. V2X has not come to reality yet, but it is on the test phase. Vehicular or vehicle to X is unknown. So X or the unknown can be vehicle. So V2V vehicle to vehicle without the help of the relay antennas. Cars can talk directly. So if there's an emergency right in front of one car, the car detects it and it sends the signals to the cars on the road or on the highway very fast without uh, having a detour to the relays on the cellular networking. So like that. Anyway, V2X and LT MIMO. MIMO means multi-input, multi-output antenna. At least two antennas for one purpose should be needed. That is MIMO antenna. Two is not enough. So I could implement 32, even 32 antennas in a compact space for KAIST in Korea for making succeeding in national projects. So they got success there. By the way, V2X antenna, uh, uh, which has LT MIMO antennas as its neighbors, they should not interrupt or interfere with each other. So interference between these two antennas, um, even though they use different frequencies, actually they electromagnetically coupled with each other. So you should suppress the unwanted interference between the different antennas of the different services. So I could guarantee this is the beam pattern. Beam pattern means the distribution, plotting of the power distribution of wireless signals in the space, especially angular space, elevation and azimuth. Elevation is usually kind of a latitude, and the azimuth is kind of a longitude. So what here I want to show you, the stick or wire antennas have some demerits or shortcomings. The far field pattern or beam pattern is desirable to send the signal to anywhere on the horizon, any direction on the horizon. But the thing is, the sticks or stick antennas or wire antennas or monopole antennas are not proper for moving vehicle. In shark fin, what we do in the past, what we did in the past was just folding them, but changing the shape, the beam patterns change, and electromagnetic functions also change. So the cautions are required. Yeah, so stick antennas are not good for wind pressures or maintenance kind of thing. So uh, here I want to compare basic electromagnetic performances of two different kind of antennas. You know, stick antennas or monopole antennas. Typically, stick antenna has this beam pattern. Meanwhile, you see this beam pattern, which looks different from what you saw in this slide. This is the typical beam pattern of the patch antenna. We want to use the patch antenna. Why? We want to have a low profile antenna for drones. You see this picture? Yeah, one, two, three, four. Yeah, all these are monopole antennas which are adopted in Jeep or Humvees, the military cars and vehicles and air ships and submarines. These stick out, so they can break it, or that means it is the maintenance cost is very high. Also, the performances are not secured. We need this kind of a beam pattern sometimes, or this kind of beam pattern is required too. How can we create this kind of a beam pattern, which originally comes from the stick antenna by the patch antenna or plain antenna? Metamaterials are the answer. So in the past, I developed the replacement of these blade antennas. Blade antennas are seen here usually aircraft blade antennas or underneath or on top, these blade antennas. Blade antennas cause a high wind resistance when they move fast. So aerodynamically, they are not designed, but they are known to have this kind of beam pattern. But with the low profile antenna like this, you can't. But by introducing Metasurface like this as a low profile patch antenna, I could make this beam pattern. This beam pattern is this is modified a beam pattern of a stick antenna. So sometimes you will hear from me about the use or the adoption of the Metasurface like this. And yeah, sorry, I need to drink coffee. And when yeah, this is a short coffee break. If you want to, if you are thirsty, please. Yeah. I took I some examples from the well-known literatures and the technical reports on antennas for drones. Still, they use this type of antenna hanging by the thread from the bottom of the drone. One, two, three, four, five, six. Well, but this must be what octocopter. What you can find that. Also, still they use even GPS antenna. GPS antenna is flat one, but GPS antenna is mounted on the top of a disc, which is supported by a stick like that. But I can change it to conformal antenna by using metamaterials. That's what I do. And also this stick antenna should be replaced. And also the beam patterns they obtained from this low periodic antenna for this drone and monopole antenna from this drone were really ugly, really ugly. So by keeping the beam patterns or improving the beam patterns and also the high profile structure should be changed to something very flat like this. As you see, there's a this is a quadcopter, but the antenna is very small. Now it's a what it confuses you, but underneath the picture, the what conformal antenna I developed with my students is almost hidden by the body of the quadcopter. Even with this structure, we have this beam pattern is called the omnidirectional beam pattern. Omnidirectional beam pattern. Also, beam steering capability has been given with the help of this antenna. It is possible. So multiple direction is much better than the omnidirectional kind of thing. Why? It is a good candidate to check the direction of the target, such as AOA or angle of arrival detection. This is there are two curves. This is a vertical beam pattern shape, and this is horizontal beam pattern shape. It has been improved to eight beam patterns, as you see. Eight beam patterns can be generated at the same time, or they can be separately generated like a beam steering capability. Both are possible by my antenna, which is very flat compared to uh, the commercial antenna. This is stick antennas, which are adopted by local mobile carrier. You can see this kind of antenna on the ceiling of the corridor in your building like that. So very flat. I had to compare the geometries of these two different antennas. And also very flat antenna, which is flexible too, which was aimed at conformity, geometrical conformity to the structure. This is the drone, but I can customize it to be attached to the underneath of the drone like this. What is so much different from what I have shown in the previous slides? This works for VHF, very high frequency. Very high frequency is not very high. It is very contradictory. Almost a century ago, this frequency was very high to hertz like that. But this is very low frequency. such as 300 megahertz, 400 megahertz. 433 megahertz, they use that frequency for the data link between the drone to the ground. It is very useful, but it's a huge pain to antenna designers. Why? VHF, the wavelength is very large, so it is really hard to make antennas small, but I could do that. I could do that by adoption of a metamaterial concept. It is a flat, so it's a what flexible. It is very flexible, and you can attach this to the chassis or body of a structure. And by using my antenna, the packet I could deliver from the transmitter. Transmitter is a drone to the receiver on the ground, almost 500 meters, 700 meters. You can see the remarkable difference between these two curves. The first curve, or the orange curve, the brown curve, is film type antenna, the first ever, and very wideband. So you can choose any frequency. In the low frequency, antenna developers can make very small antenna, such as a helix and a spiral. But the thing is, they bump into the difficulty in expanding the bandwidth to a larger one. For me, almost 110 fractional bandwidth. It was impossible before me, but I can do that. Still, conventional antennas for 433 megahertz have a bandwidth of a fractional bandwidth just less than 5% minus 110%. There's also packet frame delivery, which includes the data. It sends more data, as you see. Yeah, and drone, what the frequency was very low, right? This frequency was 2.4 gigahertz. This was much lower than that, such as 400 megahertz. But this one is 24 gigahertz. I work on millimeter wave antennas too, but millimeter wave antenna is notorious for having high path loss. The higher the frequency, the path loss really larger than that, than ever before. To increase to get over the path loss, I had to develop metamaterial lens, which is called a metasurface, so we could increase the antenna received power strength. This is a receiver, a transmitter, receiver. Right in between, you have the kind of a glass, but it is flat. Glass is a curved structure, but metamaterial is a flat structure, but it can bend the electromagnetic rays. So it can increase the concentration of the electromagnetic wave to the received area. It was the part of the project I'm working with the Korean Aerospace Research Institute in Daejeon, Korea, to put it into the drone like this, UAS. And I mentioned this before briefly. So stick antennas should be replaced by the plain antenna. The only thing we can adopt for it is metamaterial. And also the tanks, what they use VHF area, this is the VHF frequency. What you are not familiar with this kind of curve or metric, but let me tell you what this is. This is a input reflection coefficient. Reflection is the big no-no. This is the input port area, RF port. We do not like my signal get back. To get back, that energy should be consumed by the antenna, and it should be used to be electromagnetic radiation to the air. So to lower the reflection coefficient, we are happy. So like this. So minus 7 dBs or minus 10 dBs is the reference to see how healthy my antenna is. Very wide frequency. So I developed this antenna. The height is around 120 centimeters up to 140 centimeters. Compared to this, I was invited to stand on the back of the tanks before twice. It was my honor. Korean Army invited me to check the antennas they use, but this picture is not theirs. This is available on the internet this long, but they had to be changed to very short. But for the same functionality, the new antenna was needed. So I developed this prototype for them, and the beam pattern. This is omnidirectional beam pattern, and checking how wide my bandwidth is. One, two, three beam patterns at the sample frequencies observation frequencies, 250 megahertz, 400 megahertz, 450 megahertz. Beam patterns are very similar to each other. Consistency is very important too. And also we develop high frequency sensor antennas for beam steering. So Metasurface like this meta material lens, it could increase the directivity of the beam pattern like this. Without it, the beam is diverging, very large beam width, but this is a narrow beam width. This could be obtained in the past by array antenna like this, but array antenna is expensive usually. Why? When we deal with the high frequency antenna, the substrate, you see a kind of a plastic material or material. Thus, I also use the same material as the substrate. Substrate means like glass, like plastic. You can see the substrate as the electronic circuits for the computers. If you open it, the green one, or sometimes the brown one, it is notorious for increasing the loss. So loss decreases the system efficiency. So we try to avoid the use of a power divider. My group uses power dividers a lot, but for millimeter wave or high frequency, we try to avoid it. Instead, only one antenna, not using the divider, putting the metamaterial surface like this, we have a very good directivity or increase in antenna gain like that. It can be adapted to synthetic aperture radar system, which scans the surface of the Earth. These are not mine. You can refer to these literatures. Australia also is a strong powerhouse of synthetic aperture radar development to detect some natural disasters or something going on the surface of the earth like that. What I would like to tell you, antennas, you can see the reflector antenna and the SAR antenna, but reflector antenna is just for the communication to the ground. Anyway, this one is a kind of array antenna like this. It can be changed to the classic array antenna can be changed to new antennas like that. Why? It consumes less power. Less power means DC battery can go long. And also, you can make your antenna system very light. Why? It doesn't require a heavy heat sink. So it's going to be taught later too. Yeah, before taking you to the basics of electromagnetics, sorry, I'm very weird of talking later about the basics of electromagnetics. But you already know the electromagnetics 101. They are inspired by optics and physics. Lens type beam concentration and reflector type beam concentration, all they want to pursue the high directivity, as you see here, using the mirror or using the lens. What you saw here is a lens. From now on, you can see a reflector type. So planar reflector, instead of just curved, this is a parabolic surface, but it can be replaced by what the planar one. So the beam pattern, which is wide and low with the low gain, can get changed to something very good like this. So without using the active components are amplifiers. Power amplifiers are notorious for consuming a lot of DC power. DC power comes from the battery. So you know what I mean. So without using the active components, I can increase the beam gain, antenna gain by using planar structure too. And another beam what reflector, reflecting metasurface like this. This is Cassegrain type. This is offset Cassegrain, and it is also capable of steering the beam like that. And it can be applied to the change of the antenna system from the typical or conventional curved geometry to the planar one. Planar one gives you benefits or convenience. Why? You can easily deploy it and store it. But the curved geometry, cost-wise, from manufacturing to maintenance, is very expensive. That's the thing. And even satellites can hold a planar metasurface structure. It is a lens. This is a reflector. All they are based upon metasurface. Now the baseline. Sorry about that, but you know what electric field and magnetic field are. Yeah, electric field generated, it is intangible, as I told you, but it is, you can experience it while you comb your hair with your plastic comb. What your hair is attracted by something invisible. That is electric force. Electric force makes electric field, and magnet, permanent magnet or electric magnet makes magnetic field around it. So electric field and magnetic field, they are the basic essences for electromagnetics. In static electricity, static magnetism, they are separated, but they are combined in electromagnetic dynamics. That means if you want to send a signal for communication like this from transmitter to the receiver or vice versa, this is a bilateral communication system, electromagnetic wave. This is electric field and the magnetic field. They combine one power at one space, and it is propagated through the air. There, yeah, you saw my antennas, and you saw sensing. Sensing is based upon reflection and scattering. So here, these are well-known electromagnetic formulae. Ampere's law, Faraday's law, Friedrich Gauss's law, these Gauss's law called a divergence theorem. These are curl theorem. Just forget about that if you think they are tough. But anyway, current comes with magnetic field. Voltage comes with electric field. You are familiar with voltage and current in your daily lives, but actually they are based upon magnetic field and electric field. So here, instead of the wave fronts, what rays are perpendicular to the direction of the wave fronts. So easy to understand, like light. So this has your laptop has a computer, sorry, antenna. This antenna sends the signal. This is direct wave, direct wave. If you want to catch the power from the antenna and here, it is called a direct wave. But this direct wave bumps into kind of different materials. Reflection occurs between the different media or materials, air and wall or air, or glass or air and water or metal. When this is metal, it seems like a mirror, even though you cannot see what if you mirror itself is a good conductor because there's mercury which is or silver plated on the glass. So this is mirror. Actually, it is also a good conductor too. Reflection, and through with the help of reflection, you can receive the power from the transmitter when you have wall as a kind of an obstacle between these two, the direct link between the two antennas. And if there's a scatter, like curved geometry, you can scattering the field. Actually, scattering includes diffraction. I'm working on calculation of diffracted field, scatter field, and reflected field from the direct wave too. If you're interested in working on it, I can do that for you on the in terms of the project. This shows you incident wave or direct wave. It is uh, intervened by the kind of a material or structure. There's a reflection. Reflection. The application of a reflection is the reflector antenna like this, and there's a transmitted wave or refracted wave. Refraction occurs when you have a material or structure which is not a metal. Metal cuts or prevents the transmission from happening. But if there's a transmission like this, you can check the transmitted wave. What I'm going to tell you is when you try to receive the power from an antenna or target, you need reflection like this. So a direct wave and reflection. Reflection is analyzed like you imagine there's a kind of a fictitious antenna here. Actually, this is not real one. This is a real one, but this is metal ground. But if you remove the metal ground, it seems like if this is a torchlight, there's a torchlight underneath the water or mirror. So it contributes the reflected field, but this is not real, just for mathematical interpretation, especially using geometry, we understand the received power there, direct wave plus reflected wave. And we could calculate and predict the received power. Line of sight rays. Actually, if you what this is the cross sections of the building. This is a view, top view of a kind of a town. This is your campus, building 1, building 2, building 3. If you have one antenna here, kind of a base station antenna, if you your student you want to talk to him using the mobile communication service here, the beam, even though it is line of sight, the strength is somewhat good, but actually it is interfered with the diffracted field from the corners of the buildings like this. Yeah, and especially we could extract the diffracted field from the field distribution in an urban model like this. It was a 2D model, and this is a 3D model. If you want to check the electromagnetic characteristics of what airplanes on the hangar, in the hangar or airport runway, well, this kind of simulation capabilities required. So receiver side, if you move the position of the receiver, the strength is going to be smaller. Yeah. Well, there are just only 3 pages left. Yeah, just be patient, please. Yeah, this is the test setup for the direct wave from one antenna to another antenna. What the frequency is very high, 24 gigahertz. That frequency is used for radar detection. So one antenna, the other antenna, yeah, direct wave. The LOS is a line of sight, 2 meters. The energy is around just below 35 dBs. It is not bad because the input power itself is very small because we are confined in sending, giving the input power according to the national policy in the lab. But in the shielding room, that's fine. We can increase the power. But anyway, one antenna, 2 antenna, we are testing the reflection. This is a metallic body, and 1 meter, 1 meter, totally, in a total 2 meters distance, 2 meter distance. So we check how different or how similar the signal strength the receiver antenna takes for direct wave case and reflected case. So students can understand or get a glimpse of how a reflected field exists like that. And also a very interesting test, but I'm not going to tell you in detail, using different structure instead of a simple metal conductor, we could escape the beam coming to outside of the room, or the door was open, we could detect the energy there. It is the contribution of the metasurface like this. Direct or normal incidence, usually we expect a normal reflection, but normal incidence, oblique reflection like this. So that was all about my talk. Pop quiz questions are like these. Yeah, which frequency band is getting popular? What I mentioned, one frequency, very high frequency. You can give number or the name of the band for communication of via satellite. Question number two is you can calculation is not very tough here. Inversely proportional to the square of the distance. So you now have a P sub Rx. This is receive the power at 1 meter away from the transmitting antenna. If you are away from 2 meters and 3 meters, what would that be? And last but not least, the power as the product of the electric field and magnetic field. This is wireless power as the product of the E and H field from antenna. It is measured as the product of the voltage and the current. It is power, the electric power. Could you relate V and I to in this antenna problem? It is easy. Here I mentioned something here. There's a hint. So that's all I've got. If you have questions, yeah, if you want to know who they are, I can give you the answer. Thank you.
All right. Do we have any questions? The mic is here, so we should just get it around.
Yeah.
So I'm just wondering, what is the main impediment to broader adoption of patch antennas?
Yes. Yeah. The impairment means some drawbacks or shortcomings?
Yes, that's correct.
Yeah. This one is good. What it is called the broadside or bore-side beam pattern. So you see a lot of practices and products with the patch antennas. There are two kinds of popular antennas. One is monopole antenna, the other is patch antenna. But they want to, it is good for the communication upward, that's fine. But if you want to send the signal to on the horizon, actually it can. So the red means hot, the green or blue means cold or least strong. So green on the horizon means the power you received on the horizon is very weak. So if you want to give radio frequency signals to any direction of the horizon, actually patch antenna is not good. That's the thing.
So is this a geometry problem?
No, yeah. And especially geometry problem is heavily linked with the field distribution like this. Usually, this is the capture of the electric field distribution for patch antenna. But this electric field is desired for this kind of a beam pattern, like what we call this as a zeroth order resonance electric field or in phase electric field. So to have this is a typical to patch antenna. I could change this to, even though the same structure, but I could change by adding some components to change this electric field distribution to this ZOR to have this beam pattern. As you see, butterfly shape on the horizon, everywhere we have a good or equal power distribution. I think I need to visit your university anyway.
I think so too. Are there any other questions?
Yeah, good morning. Clearly, the flat antenna or the patch antenna appears like it would be really advantageous, particularly in military applications. I was just wondering, has it generated any interest? Like, is this a particular topic of fruitful discussion in Korea in terms of its utility?
Yeah, yeah. Still, what they are in the habit of using what stick antennas for omnidirectional and patch antennas for broadside like that. But Korean Army, schools of what I forgot the name of it, a school of uh, the modernization of some of the vehicles in our army, but they are interested into that. Patch antennas, still you can take the benefit out of the patch antennas like this. Each of these elements are patch antennas. If you want to shine the light towards you or in front of you or upward in one direction, this is the best. You see, this is a top a view of array antenna of patches, and this is the backside of the patch array, which has the power divider, as you see. Korean government, they know. They have invited me from academia to strategy planning team. I told them, but they want to protect the existing antenna industry. Stick antenna makers to do stick antennas, and patch antenna makers do their own thing like that.
Professor Kahng, I think you can revolutionize and create your own company and change the antenna landscape. Is there any questions?
I suppose could this be used in thinking of replacing stick antennas? Is an application potentially you could cover other aircraft surfaces with them and create like a 360-degree but very smooth contoured antenna pattern, I suppose, and then you could beam steer all around the aircraft, if that makes sense.
Sorry, I was disturbed by the phone call. Sorry. Yeah, could you repeat that, please?
Oh, I was just thinking in terms of the fact that the patch antennas can be placed flat along surfaces, so you could potentially put them on multiple sides of aircraft and then have less protrusions, and so no stick antennas required or protrusions off the surface, but where an aircraft skin naturally has a curve that faces the direction you want, you could potentially put these antennas and then steer the beams for various effects, I imagine.
Yeah. Definitely, I don't deny the usability of patch antennas and it's the modifications. Altimeter of a drone or helicopter or the aircraft, they need patch antennas, especially patch array antenna underneath on the bottom to sense the signal to the ground and the reflected field back, and using that reflected field wave, they check the distance between the ground they are going to land on. So what it is very useful also to search, because you see another practice of array antenna in SAR system, a synthetic aperture radar. All these antennas are patch antennas or slit array antennas. To scan the surface or to pinpoint the direction on the ground to talk to specifically, then it is very useful to use the patch antenna as a kind of a conformal structure. But what they do practice in the especially defense and drone area, they still want to have this kind of omnidirectional, like a apple shape or butterfly shape, which means on the horizon, it gives equal power to any direction like that. Here, my patch antenna, it is geometrically it is a patch antenna, but low profile. And even when we talk to Professor Artem Lensky or other guys in an international conference, they were interested in my antenna. It is based upon the request and requirement from Cassidian, a German aircraft manufacturer. They asked me to design this antenna. This antenna is even a little bit embedded. So this is a ground as well as the part of the aircraft surface. But my antenna is a little bit penetrated, not protruding, and even embedded there, it gives this kind of field pattern. What that aircraft manufacturer wanted to have a low profile antenna to talk to the ground. What they possibly need the patch antenna with this beam pattern, but they wanted to have a omnidirectional beam pattern like that. So they are mixed. So blade antennas are wanted to be just avoided then anyhow.
There is another question from Ashley. Just a minute.
You're busy.
So we already use electronic beam steering in combination with phased array for radars. Do you think that same type of idea could be useful for this type of antenna, to use multiple patch antennas with electronic beam steering?
Yeah, exactly.
Possibly to optimize reception in dynamic areas.
Yeah. What the antenna should not be fully metamaterial beam steering antenna. There have been several projects of mine sponsored by the Korean government and the defense company whose name starts with L here in Korea. I had to adopt the ideas of a Metasurface with the beamformer chipsets, but they didn't have to use the fully beamformer chipset working structure. Actually, beamforming chipsets are useful, which are categorized into active components which consume DC battery and which leads to heating, but try to minimize the number of the beamformer chipsets, and instead from block to block here means a sub-array kind of concept, metamaterial surface for one block, metamaterial surface for the other block, they could save the energy instead of using the full beamformer chipsets. So it's a kind of a mixed approach I could do using metamaterial with the existing phased array antenna system. Yeah, definitely, I have done it.
All right. Thanks a lot, Professor Kahng. Are there any questions online? Maybe one question from me, Professor Kahng. If you go back to your slides on computer and radar cross-section for different, yes, this one. No, I think the next slides. Yes, this one. Yeah, this looks amazing, and to be honest, I've spent about 2 weeks now working on a problem with MATLAB, trying to compute something similar. And hence the question is, one, which software do you use? Also, when it comes down, for example, to X-band radar, your mesh should be at least 10 times less than wavelength, so it's about 0.3 centimeters. So it's really computationally intense. How do you compute RCS for such complex objects, and what models do you use? Is it STL format, or can you just a little bit elaborate on computing RCS for such complex objects?
Real good, yeah. I myself am a computation electromagnetic code developer too. I have my own code, but it is very slow and it is time consuming to deal with the complicated geometry like this. I use FECO. Yeah, you can find it FEKO. Um, but yeah, FECO, you can get purchase a copy of a FECO. You can get this surface current density and the radar cross section on the vehicles you are interested in, especially yeah the wavelength as you mentioned. Yeah, entire geometry requires meshes, so meshes are very small. So in terms of the size of the mesh, actually the structure is a large sized or large scale problem. So there, parallel computing these days is possible to use, but these days lots of people know GPU, but just less than 10 years ago, GPU, using the GPU for parallel computation, it was quite early introduced there. We could take the benefit out of using the parallel computation, but not only computing power, but also the choice of uh, or understanding numerical basic core electromagnetic methods. Here, Professor Zelensky, you know diffraction, uniform theory of diffraction, UTD, or ray tracing?
I know
That's fine.
about method of moments and optical
Good, right.
and
Yeah,
FMM methods,
yeah,
but I'm not really expert in this field.
that's fine. Yeah, my original background is method of moment and ray tracing or optics. Anyway, the hybridization of different methods will give you the acceleration of the problem solving. So MLFMM, it is highly recommended. It starts from a method of moments. MLFMM is a multi-level fast multiple method. So near next to the antenna area where the meshes are very non-uniform there, and the size is very smaller. There, you need to use method of moment and FDTD, which is time domain analysis method, and and then just out of the vicinity proximity of the antenna, you use MLFMM and the cone tip. These are going to be analyzed by like a UTD, theories of diffraction. So then you can combine different methods. Actually, in the platform of FICO, you are allowed to choose the functions you are going to combine from region to region like that. I can advise you to use it too.
All right, thanks a lot. There is one more question in the chat by Craig. He's asking about, can metamaterial antennas surfaces be used to actively interfere with the reflected radar signals?
Yeah. Hopefully, the metasurfaces can be part of the radar systems. It's possible, but if you have the case to put one metasurface for example, stealth, but the other metasurface for radar, the aperture of the radar antenna, the interference, yeah, can be the problem, but the optimization work should be carried out to determine the size or spacing between one metamaterial structure with the other metamaterial used for radar systems, if they have to be put on the same surface or in the same area like that. And also, when metasurfaces, they can be also combined with the active devices such as pin diodes or semiconductor switches. The electronic noise coming from that can disturb the signal going to the radars, then you should be careful about the electronic noise there and when other stuff like that.
All right, thank you so much, Professor Kahng. Would you mind sharing the slides with us so I can disseminate here in class and other colleagues? If you could email me the slides, would be great.
Yeah.
Yeah.
As far as you keep it safely, yeah, not to going around in other areas.
All right, yeah, we'll definitely keep it just for ourselves because you've done such an amazing job. There's so many different areas that you worked on, including the defense applications and communication and radars. Yeah, I'm sure that we could find some collaborative points and projects. And yeah, thanks a lot for joining and giving this amazing talk.
Yeah. Thank you. And let me visit New South Wales, and let me have the opportunity to eat crocodile meat someday.
Absolutely, not only crocodile, but kangaroo and many things you can eat. Yeah. Yes, so many.
Thank you.
All right, Professor Kahng. Thank you so much, and yeah, I'll keep you updated, and yeah, we could have a discussion later on. Thanks.
Yeah. Thank you. And I'm leaving. Have a good day.
Cheers. Bye.
Thanks.
Thanks.
Thank you.